And this thing right here is going to evaluate to, let me think for a second. Yeah, something. Good morning, fellow mathematicians. Welcome back to another video. Once again, it's time for
Papa Flammy's random week.
Oh yeah, let's go ahead and get started. So I don't want to waste any time because, like I promised, this bitch boy right here is the climax of Papa Flammy's random week number 2. It's the monster integral I talked about. It's called Coxeter's integral, cock. And we are going to dive right in. The way I intended to present this integral at first would take me about 45 to 60 minutes to solve this thing, but maybe it's going to be less this time. So let's just go ahead and do this. And as always, I'm doing all of this out of my memory, so I hope I'm going to do this correctly. So you see we have this inverse cosine right here, and at first we would like to get rid of this thing because it's absolutely ridiculous to integrate something like this. It does look easy on first sight, but that's an absolute monster. So at first I would just like to take a look at the double angle formula for the cosine. So you know that the cosine of 2 times x is nothing but cosine squared of x minus sine squared of x. And you see by the fundamental theorem of trigonometry, we can turn this sine squared into 1 minus cosine squared, and then we can just fiddle around a little bit to get 2 times cosine squared of x minus 1. So that's the first thing we actually can do. And well, what about applying the inverse cosine now on both sides? And I'm trying to justify all my steps right here using some arguments. You see we can in fact apply the inverse cosine right here because we are on an interval from 0 to pi over 2. So the cosine is bijective on this interval, that's good, and that means we can also apply the inverse cosine. So let's go ahead and do this. So the inverse cosine of the cosine is just the argument itself. So 2x is nothing but the inverse cosine of this stuff right here. And I'm going to refer to the inverse cosine like this because it's easier to write. 2 times cosine squared of x negative 1. And why not make a little change of variables now? Let's say we have some t being equal to the cosine of x. So let t be equal to the cosine of x. And no, we are not doing any kind of substitution right now. We are just playing around a little bit with the trigonometric expressions right here. That also means that 2 times x is now nothing but the inverse cosine of 2 times t squared minus 1. But what is x? Well, since the cosine is bijective, we can just take the inverse cosine on both sides. That means x is nothing but the inverse cosine of t. So this is nothing but 2 times the inverse cosine of t. And what we can now do? Well, we can set a new variable being this argument right here. So we want this argument in the inverse cosine to be equal to z, for example. So let's do this. So that also means that we are going to end up with the inverse cosine of z being nothing but 2 times the inverse cosine of t. Well, in this case we have to solve for t at first. So if z is nothing but 2 times t squared minus 1, then t is nothing but bringing this to the other side, dividing by 2 because it's not equal to 0, taking the square root. We end up with t being nothing but positive or negative square root of z plus 1 over 2, or c plus 1, how you guys want me to say it. So we can just plug this in. So we end up with 2 times the inverse cosine of this chunk, square root of z plus 1 over 2. And well, what we can do now, we have found an expression where this thing, this inverse cosine, is dependent on some variable z, and we can express it in a different way, an equivalent way. So why not say that this argument right here, this chunk, is indeed our z, and we can plug it into here and work with it. So you might think that this right here is going to make matters worse. At the moment, yes, but it's going to make it easier in a few minutes. So what we can do now, well, you see we have this weird expression now with this being our set using the identity before, well, we can advance this 1 by 1 plus 2 cosine of x over 1 plus 2 cosine of x and bring this together to get a different expression. So we end up with 2, and this 2 was the one included with the inverse cosine. I brought it to the outside using the linearity of the integral. 2 times integral from 0 to pi over 2 of, and now we have the inverse cosine of square root. So up here in the numerator it's going to be 1 plus 3 cosine of x. And also if we advance this, we have the same denominator, bringing it together, and we can drag it down. So we have 2 times 1 plus 2 cosine of x, going to end up with 2 plus 4 cosine of x, integrated with respect to x. And this still is fucking ugly, so that's cool. So we have turned this still nicely looking expression into something way worse, including square roots and an additive denominator now, numerator. So that's not really good. But we are going to play around with this a bit more. So let's take a look at the right triangle next. So you see, if we can take the cosine of some angle phi, and we are on an interval from 0 to pi over 2, and this thing is equal to z, well, we can just apply the inverse cosine on both sides. So that means phi is nothing but the inverse cosine of z. But also on the other hand, we can say that the tangent of phi is nothing but, let's say, t. Now we can apply the inverse tangent on both sides. So that means that phi is nothing but the inverse tangent of t. So that means we can evaluate our phi equivalently using 2 different ways, either taking the inverse cosine or taking the inverse tangent. Just as a quick little side note. In a right triangle with angles being from 0 to pi over 2. That's something that holds in right triangles. Okay, cool. So what can we do with this information? Well, we can work a bit with the tangent right here. So you see, if we take the tangent of z, for example, it doesn't matter what you call this variable. Well, what is the tangent of z? That's nothing but the square root of sine squared of z over cosine squared of z. And yes, this would result in the absolute value of sine of z over absolute value cosine of z, but we are on an interval from 0 to pi over 2, so that means the absolute value of the tangent, you could say, is just the tangent itself. We are not landing at any negative values, so we are still good. Okay, cool. But what is sine squared? Well, sine squared is nothing but 1 minus cosine squared of z over cosine squared of z. And, well, what we can do now, we can just take this thing right here as our angle, you could say, as our angle z, angle phi. I'm not referring to this setup here, I'm referring to something else. So what we can do, we can plug this stuff right here in as our new argument. We can do this. So the cosine squared of z is nothing but cosine of z, but squared, same spiel down here. Okay, and now we can plug this in. Cosine of inverse cosine is just the argument itself, and the square root squared is just this argument right here. So this is basically what we are going to end up with. So we end up with, with the square root of, what do we have? 1 minus 1 plus 3 cosine of x over 2 plus 4 cosine of x over 1 plus 3 cosine of x over 2 plus 4 cosine of x. I hope you can see where all of this came from, so that's quite a mindfuck right here. It's, it's something really hard to swallow. I hope you can still follow me. And now we can just advance this fraction right here by 2 plus 4 cosine of x over the same thing. And we are going to end up with the square root of. So up here at first we have 2 minus 1, so this is just 1, plus, and well, 4 minus 1 cosine of x is just the cosine of x. And you see, if we advance this fraction, this is 2 plus 4, and this is going to cancel out. So in the denominator we just have 1 plus 3 cosine of x. And now we are on an interval 0 to pi over 2, so that means we can safely take the inverse tangent right here on both sides. And then we have an equivalent formulation for our angle z right here, which is just this whole thing right here, our integrand. Whew. And now we can finally start evaluating this integral right here. So what we have done till now is just some fancy footwork to turn this into something else, because we can actually work with the inverse tangent. We have derived formulas before to express this inverse tangent as something else. But I'm going to come to that point in a minute. You see, this integral right here is as trivial as my t-shirt right here. Please share my videos everywhere. This thing needs to get viral. That's an absolute monster. It's fucking dope. So, in the next step, I would love to make use of the double angle formula once again. So, how can we do that? Well, we can just introduce a new parameter. So let's say this time it's resubstitution. So let's x be equal to 2 times t, which also means that dx is nothing but 2 times dt, well, dividing. No, we don't need to divide, we can just substitute in. So we are going to end up with 2 times. Okay, now we have new upper and lower bounds. If we plug in x equals to 0, well, that's the product. 2 isn't equal to 0, so it means t needs to be 0. And well, if we plug in pi over 2 into x, well, dividing both sides by 2 not equal to 0, we end up with an upper bound of pi over 4. Now we have the inverse tangent right here of the square root of. Okay, what do we have now? 1 plus cosine of 2 times t over 1 plus 3 cosine of 2 times t. And now we have 2 times dt. Well, we could in fact bring this 2 to the outside right here to turn this into a 4. 2 times 2 is 4, if you can trust the piano axioms. And well, now we can once again take a look at the double angle formula right here. So remember, just like before, cosine of 2 times t is nothing but 2 times cosine squared of t minus 1. And we can actually plug this in here. And you see, if we just add 1 on both sides right here, that's actually quite handy. That's why I wanted to introduce this double angle formula, because we can get rid of this numerator right here. Just adding this on both sides, we are going to end up with 1 plus this stuff being just 2 times cosine squared. We can plug this into here. So at first we end up with 4 times integral from 0 to pi over 4 of the inverse tangent. So now we have the square root of this chunk, 2 times cosine squared of t over, and now we have this thing right here. We can rewrite this thing right here equivalently as, so cosine 2 times t is nothing but this chunk we had before, but it's also 1 minus 2 times sine squared of t. And I want to write it in regards to the sine right here, for reasons that will become obvious later on in the game. So let's just plug this stuff into here. So now we have 1 plus, and now 3 times this chunk right here. So this is going to result in 3 minus 6 sine squared of t, integrated with respect to t. Like I said, I still have to think about all the steps because I don't have any notes right here at the moment. And you see, this is going to be a 4 down here, and in fact we can factor out the 2 right here to get rid of this 4 and the 6 to turn this into a 2 and a 3. So let's write it here. So we have 4 times the integral from 0 to pi over 2. And those are some dope-ass manipulations. Inverse tangent of square root cosine squared of t over 2 minus 3 sine squared of t, integrated with respect to t. And you see, in fact, the square root of the cosine squared is just the absolute value of the cosine of t, but we are on an interval from 0 to pi over 4. That means cosine won't take any negative values. So that in fact means that we can just take the regular cosine instead of the absolute value. All of this in the next step, and we are going to take a look at something different than the inverse tangent. So we are going to turn this into something else. Like I said, we would like to turn this inverse tangent into something else. And we want to consider this thing being not with respect to any variable at the moment. So let's say this stuff right here is constant at the moment. Well, we have a certain formula right here. I have used this extensively before. So you know, we can take a look at 1 over a, you could say, inverse tangent of 1 over a. This should seem pretty familiar to you guys. We are using this all the time when evaluating integrals, all sorts of integrals. It's one of the most important integral identities I know of, in my opinion. So, you know, this is nothing but, well, 1 over a, inverse tangent of x over a, but evaluated from 0 to 1. So lower bound, inverse tangent of 0 is just 0, so that vanishes, and yeah, this one, you see it's up here right now. And we can actually express this thing right here as something completely different, namely as the integral running from 0 to 1, that's why we have an upper and lower bound, of dx, you could say. Going back to x, it doesn't matter what you call those variables, dx over x squared plus a squared. This is, like I said, an identity we are using so often right here on this channel, and now we can multiply both sides by a. We don't want it to be equal to 0. No, that equivalent sign is just... Never mind. So right here we have an a now, and I want you guys to consider this thing right here, this argument of the inverse tangent, as 1 over a. So now we can make use of this identity up here to turn this into something completely different. Let me put this up here so that I can take a look at it. So we end up with 4 times an integral from 0 to pi over 4 times an integral. Okay, so we still have this a, but a is nothing but 1 over a, so we just have to take the reciprocal of this thing and bring it to the front. So we have square root 2 minus 3 sine squared of t over the cosine of t, and this integral is running from 0 to 1, and also times this dx, you could say, in the end. So in the end we are going to end up with a dt right here, but with an dx in front, because we have to evaluate this integral at first. We turn this into a double integral. So what do we have? We now have this 1 over, now we have x squared, and then we have the reciprocal of this thing right here, but squared. So this is just plus 2 minus 3 sine squared of t over cosine squared of t in this case, because it's squared. Okay, that's really, really interesting. So we have a double integral now, and it really looks like it would make matters way worse. But it's not, it's actually quite nice to evaluate this. It's absolutely fantastic. So what we can do now, well, since those are constants, why not bring them a little bit to the outside? So we have this 1 over cosine squared of t. Let's bring it to the outside, factor it out on both terms. So we end up with x squared times cosine squared of t. But we have this factor of 1 over cosine squared of t. Turning this around, bringing this cosine squared here in the numerator, cancelling out with this cosine of t. I'm not going to spare you guys. No mercy from Papa here. When you watch something like this, you have to deal with all the facts not being written out. So we end up with 4 times integral 0 to pi over 4. Integral 0 to 1. Now we have square root 2 minus 3 sine squared of t times. Now, like I said, this and that is going to cancel out kind of, so we end up with the cosine of t in the numerator up here over x squared cosine squared of t plus 2 minus 3 sine squared of t dx dt. That's a lot of things you have to swallow right now, but trust me, it's going to be worth it in the end. Okay, coolio, and you know cosine squared is nothing but 1 minus sine squared. So let's put it here. 1 minus sine squared of t, and we can just factor this out a little bit. So we end up with I'm sorry, I had to cough. So we were here, yeah, just dx dt. I'm terribly sorry for that. And what we can do, we can just factor out this sine squared, you can say, and bring those terms a little bit together, and then we can move on with the next step. Let me just quickly write everything out once again. Here. And now we can move on with the next step. What else could we do? Well, you see, it would be absolutely nice to get rid of the square root up here. So that's really fucking annoying right now. What we could do, we could turn this into 1 minus cosine squared right here. So that's something we could do, but we would still end up with this factor of 3 right here, which would fuck everything up. But what we can make use of, well, we can introduce a clever substitution. Because in one strike we could factor out this 2 right here. And we could get rid of this 3 right here. Just follow my thought process here. So why not let our sine of t be equal to the square root 2 over 3 sine of phi. I hope you can see where this comes from. So if we square this right here, well, we could get rid of this 3 right here, cancelling out. And also we could factor out our 2, and then we have 1 minus sine squared, which is nothing but cosine squared, and then we could have another expression for the cosine, because we could use the square root on the squared. So that's quite a clever substitution, and we are going to move on with this now. So, let's move on, and right now we are only dealing with this outer integral, you could say, so we are not laying a finger on this inner one, which was the inverse tangent a moment before. So just keep this in mind, because now we have to differentiate this. We did a substitution, so this means we end up with cosine of t dt being nothing but square root 2 over 3 cosine of phi d phi. There we go. We are defying the system of mathematics once again. I'm the mathematical evil overlord. Yeah, and we can plug all of this stuff in. And you see the cool thing is cosine of t dt is nothing but this thing right here, so we can just plug this new value into here. But now I want you guys to take a look, that's why I said this little sentence before, at the upper and lower bounds, because we are only dealing with the outer integral, which was with respect to t before. So we end up with 4 times integral from, well, if you plug the lower bound in, sine of 0 is something that's non-zero times something, so this something has to be 0. And also, if you plug pi over 4 into here, you can use your calculator. Sine of pi over 4 is nothing but 1 over square root of 2. So that means we can multiply both sides by this term right here, this non-zero term, and then solve for phi using the inverse sine. We are on a certain interval, so we can do this, use the inverse sine, and you are going to end up with pi over 3. I don't know if I'm going to include this in an outtake. Maybe I will, I'm not certain, but that's child's play, to be honest. So, and now our integral, 0 to 1. Integral of 2 minus 3, and now we are going to square our sine of t, which is nothing but square root 2 over 3 sine of phi. So that means we have 2 over 3 sine squared of phi. And you see, like I promised, this is going to cancel out. We can factor out the 2 on both terms. That means we have 2 new square roots that we can drag out a little bit. That's just multiplicative and positive inside the discriminant. And also cosine of t dt is nothing but this chunk right here. So we have square root 2 over 3 cosine of phi. I'm going to bring this dx d phi right here over. Okay, now we have x squared plus 2 minus. Now we have this chunk right here, which is nothing but 2 over 3 sine squared of phi x squared plus 3. So we have written out a lot of things right now, so that's quite cool. What we can do, we can factor out this 3 right here on both terms, and then we have, if we bring this square root of 3 down here in the denominator, we have 3 over square root of 3, which is nothing but square root of 3. You can advance this fraction by square root of 3 over square root of 3. That's a lot of stuff to say. Yeah, indeed. And also you can bring the square root of 2 to the outside also. Let me conclude what I just said. So we have 4 times integral from 0 to pi over 3. Integral from 0 to 1. Also we are going to have the square root of 3 term right here. Let's put it here. Up here in the numerator. Well, like I said before, we want to factor out this 2. So we are going to end up with a square root of 2 up here. And then we have the square root of 1 minus sine squared. But 1 minus sine squared is nothing but cosine squared. Cosine squared of phi. We are on an interval from 0 to pi over 3. That means that thing would be the absolute value, but it won't take any negative values. So that means that's just a regular cosine. That's a lot of erasing right here, but also we still have our cosine of phi and the square root of 2. So we can bring this together as 2 times cosine squared over. Okay, so we have factored out this 3 right here. So we have 3 times x squared plus 6, this right here. I hope you still remember. And now we have negative 2 times. Okay, negative 2 times sine squared is nothing but 1 minus cosine squared. So let us write everything with respect to the cosine right now. So this is 1 minus cosine squared of phi. And then x squared plus 3 dx d phi. So there was a lot of rewriting and stuff like this, and now we can do some more cosmetics. I'm going to write everything out again. We already came such a long way, and this right here is looking way more advertiser friendly and family friendly than this inverse cosine of cosine stuff we had at the beginning. So you see we had the square root of 2 times square root of 2 up here. It's just 2 times 4 is 8. This stuff, you can also bring this 8 times square root of 3 to the outside if you like. You can do this using the linearity of the integral. Saying linearity is hard. Also, I cancelled out a lot of stuff. So you see, I factored out everything, and the 6 and negative 6 is going to cancel out. 3x squared, negative 2x squared cancelling out. We have this stuff right here, right now. And well, now I would just like to introduce a rather famous substitution, you could say. I would like to turn this into something algebraic. So turning trigonometric stuff into algebraic stuff makes things easier most of the time. So why not let our u, for example, be equal to tangent of phi in this case. It's going to come in quite handy because if we differentiate the tangent, we are going to end up with the secant squared, but secant squared is nothing but 1 over cosine squared. Ta-da! We have the cosine squared right here. So it does make sense actually that we introduce something like this. So that means du is nothing but secant squared of phi d phi. But what is secant squared? By the fundamental theorem of trigonometry, this is nothing but 1 plus tangent squared of phi d phi. But what is tangent squared? Well, tangent is nothing but u, so this is 1 plus u squared. Then we can divide both sides by 1 plus u squared. Never ever gonna be 0. So then we end up with a final expression for d phi. So that means that d phi is nothing but du over 1 plus u squared. And you see, 1 over 1 plus u squared is nothing but 1 over secant squared, which is going to result in the cosine squared. So we also have an equivalent formulation for our cosine squared right here. And remember, we are only dealing with the outer integral at the moment all the time, so we haven't done anything with this inner one till now. So we have to change the upper and lower bounds of this integral respectively. So we end up with, bringing this to the outside, 8 times square root of 3 integral from, well, tangent of 0 is just 0, and tangent of pi over 3 is square root of 3 as a matter of fact. So type it in your calculator or something, or Wolfram Alpha, I really don't care. So square root of 3, and an integral from 0 to 1 of, like I said, cosine squared is nothing but 1 over 1 plus u squared. Also, our d phi is du over 1 plus u squared. This inner integral isn't with respect to u, so we can treat it as a constant and bring it to the inside, you could say. So we still have this over, so we have this 1 over 1 plus u squared dx du. I hope you can see why I did this actually. And now we have this x squared plus 2 times 1 over 1 plus u squared. Okay, x plus 3. You see, we can distribute this 1 over 1 plus u squared into here to get rid of this thing right here. But don't forget to multiply it by this, and also we have to multiply everything by this right here, resulting in another little expression right here for this double integral, 8 times square root of 3. Same upper and lower bounds, 0 to 1. And now we have, I'm going to put the dx du right here. So we have 1 over. We have this right here squared on this term right here. But we can factor one of those out, you could say. So we end up with 1 plus u squared times. And then we have 1 plus u squared times x squared. So this is going to result in u squared times x squared plus x squared. And also we have this term right here times this because this and that are cancelling out. So we can just factor out this term like we did here. Just take a piece of paper and write it out. I just can't write everything out because it would take just too much fucking time. My head would explode right here. So in fact we are going to end up with plus 2 times x, and there's a square missing right here, I'm terribly sorry, x squared plus 6. So that's just what it's going to be at the moment. And we can bring those two together actually to end up with 3x squared. And you see, now we have 1 over factor times factor, and those factors are with respect to u, you could say. So why not do some sexy partial fraction decomposition a little bit? And also it would make sense to interchange those integral signs right here. I don't really have an explanation why we can do it. I'm Papa, so I'm just going to do it. Yes. Ugh. So, sorry I didn't announce that we are going to do a little outtake. I totally forgot about that this time. And oh my guys, I'm going to announce the meme. Never mind. So I've written everything out that we have gathered in the partial fraction decomposition. I have used the linearity of the integral to break this up. I hope you noticed that we have just interchanged the integral signs right here. That's the only thing I don't really have an explanation for why we can do it. Let's just do it. And yeah, also dx, du, interchange, breaking this up, blah, blah, blah. This term, this common factor isn't with respect to u, you could say, so we can just bring it to the outside. And now for some evaluation. This thing right here is actually quite easy to evaluate. This integral is nothing but the inverse tangent from 0 to square root of 3. Inverse tangent of 0 is 0, so this is going to vanish. Inverse tangent of square root of 3 is pi over 3. So this right here is pi over 3, all in all. But what exactly is that? Well, we can't really do anything with it right now, because we don't really have it in the proper form at the moment. You see, if we would just have 1 over u squared plus something squared, we could do this, but we have u squared times x squared. So why not factor out x squared on both terms? So this is going to cancel out actually, so that's quite good. This is going to cancel out, and this is going to cancel out. And we only have this in the proper form if we take the square root of this whole term right here, this constant term you could say, and square it once again. So that's what we mostly do with this kind of thing. And now we are going to end up with an ugly looking inverse tangent. So we have to take the reciprocal of this thing right here. And you see we would have the square root of x squared, but we are on an interval from 0 to 1, x only taking positive values, so the absolute value of x is just x once again. So we end up with the reciprocal of this thing. So this is x over square root 3 x squared plus 6. Okay, and what else do we have? Well, we have the inverse tangent. So this is the same we had before, this 1 over a times the inverse tangent of x over a from 0 to 1. So that's basically the same situation, you could say. And also we have the inverse tangent of this chunk right here times u right now. U times x over square root 3 x squared plus 6, evaluated from 0 to square root of 3. Yeah, okay. Now we have this. If we plug in 0 into here, this whole thing is going to vanish. So that's actually quite cool. My cable is hanging down right here actually. Let's put it in once again. And if we plug in square root of 3, well, it's just what it is. And you know, we could factor out a 3 down here. So this in the denominator is nothing but square root 3 times x squared plus 2. So this is something we can actually do. Same thing we can do here, and we can break this up. So this takes positive values, and this is positive. Now we can take up this third, the square root. Yeah, and if we plug in square root of 3, this and this square root is going to cancel out. What we end up with, finally, and also we can bring the square root of 3 into here. Let me conclude everything. Now we have 8 times square root of 3, integral 0 to 1. We have this first part, pi over 3 times this stuff right here. So we have pi over 3, 1 over 2 times x squared plus 6. So this has been the first part. Also, we have this negative sign right here. So we end up with negative. Okay, now we have a lot of stuff we have to consider. So the square root of 3 and this is going to cancel out. We can bring this 8 into here. So we have integral 0 to 1 of 8 times x over. And now we have square root x squared plus 2. So this reduces quite nicely and we have this stuff right here. So we have the inverse tangent of, okay, so this is going to evaluate to x over square root x squared plus 2. And well, that's basically it. Don't forget your dx's. I totally forgot about them. So here's a dx, here's a dx. And this is the form our integral is going to take now. And we can actually evaluate that, and also square root of 3 over 3 is nothing but 1 over square root of 3. So you can simplify it like that, and we can also cancel this 8 out with the 2's down here, so that's also something we can do. Excuse me for that. I totally, I said that we have to be cautious, but I forgot this term right here, putting it here. Still, I'm terribly sorry. Hey, coming in from this side. So I'm terribly sorry for this little part right here. I hope this was the only error I did in this whole process of evaluating this thing. Like I said, I'm doing this all from stake, improvising this right here. So it's really an absolute monster right here we have to evaluate. So I'm sorry for any mistakes I made in the process. But just like before, I factored out this 1 over 2 right here on this one term I forgot and turned this 8 into a 4. 8 over 2 is just 4. Okay, cool. And you see we had this integral right here, and I made some little manipulations because 3 is nothing but square root of 3 but squared, so that we can indeed use our inverse tangent identity we had before. So this is going to be 1 over a, so 1 over square root of 3, inverse tangent of x over square root of 3 from 0 to 1, and as a matter of fact, inverse tangent of 0 is just 0, and inverse tangent of 1 over square root of 3 is nothing but pi over 6. So we have 1 over square root of 3 times pi over 6. So coolio, we've evaluated this. But what about this right here? So, are you kidding me, Papa Flemmy? So that thing right here looks absolutely terrifying, but it's not, to be honest, because now something absolutely golden is going to happen, something really fappable. I'm sorry for this. So what we can do, we can actually use integration by parts on this one right here, and it's going to turn into something absolutely familiar. So we need to differentiate something and we need to integrate something. Plus minus. Why not differentiate the inverse tangent right here? The inverse tangent of x over square root x squared plus 2. I'm going to put this into an outtake, I guess, how to differentiate this thing. Or have I done this before? I can't remember. Never mind. And yeah, on the other side of things, we have to integrate this right here. So x over x squared plus 3 square root x squared plus 2. And as a matter of fact, this is going to be included in the outtakes. This thing right here is nothing but the inverse tangent of square root x squared plus 2. And this thing right here is going to evaluate to 1 over, so differentiating this is really quite easy, 1 over x squared plus 1 square root x squared plus 2. And well, multiplying this together, taking the integral of this thing, and putting my cable in once again, which is sliding out of my pocket all the fucking time, we can evaluate this actually. So we end up with this chunk right here. So 1 over square root of 3 is nothing but 3. So this is going to evaluate to 4 times pi squared over 18. But this is nothing but 2 times pi squared over 9. So this is 2 times pi squared over 9. Now we have this thing right here. We have this negative sign. So negative 4 times inverse tangent of x over square root x squared plus 2. Inverse tangent of square root x squared plus 2. Okay, evaluated from 0 to 1. And I want you guys to notice something. If we have this 0 right here, this first term is going to absolutely vanish. And if we evaluate this at 1, well, this is inverse tangent of square root of 3. And this is the inverse tangent of square root of 1 over 3. So inverse tangent of square root of 1 over 3 is nothing but 1 over square root of 3 is nothing but pi over 6. So we have evaluated this before. And this thing right here is going to evaluate to, let me think for a second. Yeah, something. I actually had to look this up right now in Wolfram on my mobile phone. I'm terribly sorry, I'm fucking stupid. This is evaluating to pi over 3. I'm so sorry for this. And also, what else do we have? We have negative 4 times this chunk right here with the negative signs cancelling out. So positive 4 times integral from, and here's the best part of it all, 0 to 1, of, and now we have the inverse tangent of square root x squared plus 2 over x squared plus 1 square root x squared plus 2 dx. And you see, this right here is going to evaluate to 4 times pi squared over 18, which is 2 times pi squared over 9. This is going to cancel out actually. So I'm fucking stupid. I don't know why I had to look this up. I just could have calculated this through. Never mind. So we end up with 4 times this thing right here. We are done, my boys. So we are actually done because we have evaluated this bitch boy right here before. You know, this is nothing but Ahmed's integral. So we have reduced this absolute monster of an integral, Coxeter's integral, to Ahmed's integral, but 4 times. So our big motherfucking cock-sucking solution right here, conclusion, is that I is nothing but 4 times Ahmed. And what was Ahmed? It was something like, this is 4 times 5 times pi squared over 96, something like this. If I remember correctly, it was some really odd value. 4 over 96 is 24, so we end up with 5 pi squared over 24. And that's why I have evaluated Ahmed's integral at the beginning of the week, because I wanted to reduce this absolute bitch boy from today to this integral to surprise you boys a little bit. I'm terribly sorry for the 1 or 2 mistakes I made in the end. This recording, let me see, is exactly going on for 1 hour and 13 minutes at the moment. So I'm terribly sorry for that. But you see, if you talk about one thing all the time, it's just going to be a fucking mess. My camera is blinking right now, so the recording is going to stop. I wish you guys a fantastic day, and up until the next video, have a flammable day. See ya! So, I'm terribly sorry. So, like I said, I ran out of camera space on my SD card. I thank you guys for watching. I hope you did enjoy this extra long video. It took really long to record this in one session. If you want to get the t-shirt I wore a second ago, then feel free to buy it. Down there in the description, link will be there. You can support the channel this way and also support me on Patreon if you like. I hope you did enjoy this video, and please share the stuff everywhere. So this week was the most effort I ever had with an integral week or something, so I would highly appreciate you guys sharing my stuff everywhere so that we can increase our little family right here. See ya!